Good day, Doctor. I am Rabaka Tabapelu here to present to you the design of infinite impulse response filter. Introduction. The infinite impulse response filter is a recursive filter in that the output from the filter is computed by using the current and previous inputs and outputs. Methodology. These are steps and methods that led me to a workable solution. I have calculated the quantification error, calculated poles and zeros. I have calculated also the IIR coefficients. I have sketched the border plot and finally implemented the basic structure of IIR filter on LabVIEW. Quantification error. So for quantification error, our maximum voltage is 5 volts and we have looped our program to a value of 1024, which in this case is represented by 2 to the power of 10, where the 10 is our bit numbers. And the value of quantification error we have calculated is 0.049, and this is our step size. Results of the poles and zeros. For poles, I have used 160 Hz, which was the signal frequency. I have multiplied it by 2 pi and divided it by 500, which is the sample frequency, to obtain an angle of 2.01. Using this angle, we have calculated the opposite and the adjacent so that we can work towards obtaining the pole 1, which is negative 0.3 plus j multiplied by 0.640. So the pole 2 is just the ghost image of pole 1. It's also a conjugate pair where the j in this pole 2 becomes negative. For zeros, we have used 205 Hz, which was the noise frequency, multiplied by 2 pi divided by 500, which is the sample frequency. The sample frequency of poles and zeros is the same. Using that 2.58 angle, we've calculated the opposite and adjacent side. That led us to obtaining 0.1, which is negative 0.846 plus j multiplied by 0.533. For 0.2, the 0.2 is obtained by taking the conjugate pair of 0.1, where the j becomes negative. Pole 0 location on S-plane. The pole 0 location, there's pole 1, pole 2, there's 0, 1, 0, 2. Pole 1 and pole 2. Pole 2 is the ghost image or a conjugate pair of pole 1. Pole 1 is negative 0.3 plus 0.640, which that means we've moved up across the j omega axis by 0.640, and we've moved across the real part to the left by 0.3. And pole 2 is negative 0.3, negative j 0.640. That means we've moved across the real part to the left by 0.3, and we've moved across the j omega axis downwards by 0.640, where the j is negative. On the outer circle, there's zeros. There's 0.1, which is negative 0.846 plus j 0.533. That means we've moved across the real part to the left by 0.846, and we've moved across the j omega axis upwards by 0.533. Its conjugate pair will be 0.2, which is in red, where the J will now be negative. That means we've moved downwards across the J omega axis by 0.533. Results of IIR coefficients. Here we have substituted the zeros and poles we have obtained in the IIR equation, and afterwards we solved the equation in order to obtain the IIR coefficients, where B0 is 1, B1 is equals to 1.692, and B2 is equals to 1. Those were the coefficients of zeros, and the pole coefficient is going to be A1 is equals to 0.6 and A2 is equals to 0.5. Board plot with FFT simulation. FFT stands for fast Fourier transform. The blue line here, which is representing the board plot which represents the low pass filter. Here I have made the amplitude and offset of both the signals to be the same to prove that my filter is filtering out the unwanted frequency. The wanted frequency which is to be extracted is at 160 Hz, and the unwanted frequency which causes disturbance, which is noise frequency, is at 205 Hz. The board plot is going down, starting from the frequency that is supposed to be extracted, which is at 160 Hz, and is going to filter out the frequency that causes disturbance at 205 Hz, where there's a highlight with a red circle. Lab view structure. This is the structure that I have implemented on the lab view to work towards my solution. Here there's B1, there's B0, there's B1, there's B2. I have substituted the coefficients I have obtained from the equation of IIR. There's also negative A1, negative A2. In there I have substituted the coefficients I have obtained from the equation of IIR, where in this case they are affected by the negative on the A1 and A2. There's also simulate signal, which is representing the signal that is wanted, which is the 160 with an offset of 2.5 and an amplitude of 2.5. The simulate signal 2 contains the specifications for a signal that causes disturbance, which is noise, of 205 Hz with a voltage of 0 to 1 and with a sample frequency of 500 Hz. Here we have our program looped to a value of 1024, which was represented by a 2 to a bit to a power of bit 10 in the quantification error. Here there's noise frequency graph, there's signal frequency graph. There's two graphs represents or will display the signal that has the noise on it, and will display the other signal that has no noise, which is the wanted frequency.